Hi everyone and welcome to my YouTube channel. We're continuing our inequalities playlist, and in the last video we took a new inequality. After we discussed the AMGM, we discussed the Muirhead inequality and we solved some beginning examples just to know how Muirhead is useful in inequalities in general. In this video we'll be solving more advanced problems on Muirhead. We'll be basically solving just two examples. The first is a classical example, but the second one is challenging IMO problem 3. So what are you waiting for? Let's get started. Our first example for today is the very classical question that you will see in nearly all math inequality books, and this inequality is called Nesbitt's inequality. So let's begin with that. This is Nesbitt's inequality, and the reason this is really a famous classical inequality, it's not just solved with Muirhead but nearly with all other inequalities. So you will see this inequality appearing in nearly all inequalities. Like it can be solved with Muirhead, with Cauchy's inequality, with tons of other inequalities and other methods. Today, of course, we'll be exploring how we can solve it with Muirhead. So let's do that. First of all, the question is the following. We need to prove for ABC, positive ABC, the following: sigma A over B plus C is greater than or equal to 3 over 2. So this is basically the Muirhead inequality. Okay, so let's begin our solution. So if you remember in the previous lessons, when we did Muirhead, we most of the times just had some polynomial on the LHS and a polynomial on the RHS here and here, something like sigma, let's say A to the something, B to the something, and C to the something. And here the same thing. And then we just did the majorization thing, and we were done. Here, as you can see, we have fractions. We don't have polynomials here. So what does that mean? We need to get polynomials by simply expanding. So this is actually or actually nearly the only bad thing about Muirhead is that you really need to expand. And expanding sucks, really. It's boring, and there's a great possibility that you're going to mess up. So that's why we need to be very careful. And you should be quick. You need to have accuracy, because you don't want to get wrong expansion, as this will give you you will basically lose lots of time, and you will not get, of course, a solution. And at the same time, you don't want to spend forever, so you need to be fast. We will try our best to illustrate how expanding in contests works, and this actually will be clarified in the next problem. But anyway, let's see how we're going to expand this one. So first of all, as you can see here, in order to expand this, it's the plan is super simple. We're just going to multiply both hand sides here, the LHS and the RHS, by pi B plus C. So if you multiply by that, we can get rid of the fractions, and let's just do that. So we have our inequality is the same as sigma A times A plus C, or A plus B times A plus C. This is greater than or equal to 3 over 2, and pi A plus B. Alright, so how can we expand this in a fast way? Well, let's do that. Okay, let's look here. Of course, the beautiful thing is that you just need to expand one of them, and then the sigma, you can just literally expand the sigma for all of them. So for example, here if you multiply this by this, you get a cube. So that means you get sigma a cube, and so on. Okay, so how can we expand this? Well, just look at this one here. This is really simple to expand. It's just going to give you 4 terms. But even like simpler here, if you just look at this, this is by the way, is going to give you a degree 3. Like everything is degree 3 because everything is homogeneous here. So you can easily see that you're going to get a cube. So that will give you sigma a cube. And then you're just going to get, if you apply any like a times b times c, you're going to get abc. So this is will give you, of course, sigma abc is just 3abc. And the rest is just a square c and a square like this b. So this is basically sigma a square b and sigma a square c. So this is basically just sigma symmetric a square b. So guess what? This is just the expansion of the LHS. We're done. It's that simple. It's just like, as we said, a cube here, and you get the sigma. You don't need to expand the other guys. The same thing here, a, b, c. You're going to get sigma abc, which is just 3abc. And a times c is a square c. And a times b is a square b. So this just can be included in the sigma symmetric. All right, very good. This is the LHS. Let's now expand the RHS. So we have 3 over 2. Let's do the expansion here. Okay, what is pi a plus b? Think about it. This one is also degree 3. Everything is degree 3. What are we going to get by pi a plus b? Of course, we're going to get a terms. If you think about it, you can get actually a, b, c, and another a, b, c. You can get it in 2 ways. If you start with a, you have one way, and if you start with b, you have another way to get a, b, c. So that means we're going to get 2 a, b, c here. All right, now we have 6 other terms. What are they? Well, simple. It's just like we're going to easily get a square b. So this one is symmetric. So it's going to be symmetric, sigma symmetric a square b. You really need to keep this thinking in your mind because expanding will really be fast. So, for example, this thing here is for sure symmetric because we have a plus b, b plus c, and c plus a. It's a product here. So this is symmetric. So if we just get a square b, that means we're going to get also a square c, and we're going to get a b square and a c square and all of the other guys. So this is basically sigma symmetric a square b just because we got a square b. Alright, and of course always keep an eye on the number of terms. So here we have 2 times 2 times 2, so it's 8 terms. So this is how many terms? 6 terms, and this is 2 terms. So we got 8 terms. So that means for sure we are correct. Okay, so right now we're basically done with that. Now we can simply begin by canceling stuff. So right now let's get the 2 out there and the 3 out here. So first of all, we're going to get here 2 sigma a cube on the LHS and 3 times 2 here and 2 times 3 here. So they will actually cancel the ABC. So now we just have 3 sigma symmetric a square b and here 2 sigma symmetric a square b. So that just means we're getting the following. Alright, now this is a simple inequality. Of course, here now we have a polynomial with the LHS and a polynomial with the RHS. So now this is the perfect time to apply Muirhead. And of course, this is really simple. Just consider the following: 3, 0, 0. And consider here 2, 1, 0. You can easily see that this majorizes this because they have of course the same sum. And 3 is greater than 2, 3 plus 0 is greater than like 2 plus 1. Of course, it's equal to it. And that's it. Basically, we're done. Alright, so that was one way to solve or to prove the very standard Nesbitt inequality. Of course, this one will appear a lot, so maybe we'll actually be revisiting Nesbitt's inequality, but we'll be revisiting it for other techniques, like maybe for Cauchy in our next lessons. Okay, so that was our first classical question. As you can see, Muirhead is all about you need to expand, and after you expand, you simply cancel stuff, and at the end you just apply Muirhead somehow. Alright, now we'll be going for the IMO problem 3. Alright, so let's go now. So this question actually appeared in the IMO 2005 problem 3. Let's see. So in this question, they're giving us 3 numbers, x, y, z, 3 positive numbers, such that we have x, y, z is greater than or equal to 1. So we have a condition here. And we need to prove the following inequality. So sigma x to the 5 minus x squared over x to the 5 plus y squared plus z squared is greater than or equal to 0. Alright, that's it. Okay, so looking at this question, 3 positive numbers, okay, that's cool. We have a precondition here. It's a bit weird. We have x, y, z is greater than 1. It's not like it's equal to 1. And then we have, we need to show this thing here. Of course, the first thing you should look is like here. If you noticed, we have here degree 5, degree 2, degree 2, degree 2, degree 5. So is this homogeneous? For sure, no. And what do we do when we have like a non-homogeneous inequality and we have a condition? Well, you guessed it. We simply try to homogenize it and get rid of the condition. However, how can we get rid of this condition? It's x, y, z is greater than 1. It's not like it's equal to 1, so we can always substitute x, for example, as like 1 over yz or something, or like try to decrease the degree of this, let's say. We need to be careful here because we have an inequality. We cannot just say it's equal to. Okay, so let's have a look. Here we have degree 2, degree 2, degree 2. And here we have degree 5, degree 5. So one way we can think about is to try to make this degree 2 and this degree 2. So how can we do that? Well, here we have x to the 5. So one idea is to do the following. Since this is an RHS inequality like this is greater than something. So we're minimizing this. So we can just say x is greater than 1 over yz from here. And we can take this x to the 5, make it x to the 4 times x. And if we apply this now, we're making it x to the 4 over yz. So now this thing here is degree 2. And this is degree 2, so this is perfect. Okay, so this is like a great trick here. But the problem is for this thing here. Can we do the same thing? Can we do that this thing is greater than x to the 4 over yz? Well, unfortunately, no. The reason is simple. Here, it's like we need to minimize all of that. So we need to minimize the numerator. But that doesn't mean we need to minimize the denominator, no. Actually, we need to have the opposite. So this unfortunately doesn't work. Okay, so what can we do? How can we homogenize this one? It's a bit tricky. Okay, so let's have a look at our fractions, this thing. You should look at this and notice something nice. Look here. The denominator is x to the 5 plus y squared plus z squared. The numerator is x to the 5 minus x squared. Well, you should notice that these guys are the same. So, what can we do? We can partition the fraction. This should be a direct thing that should always come to your mind. This idea is really appearing a lot in math inequalities in general. Like in math Olympiad contests, whenever you see a fraction and you notice that the numerator and the denominator they have something in common. Sometimes if you have something like this, sometimes you can just add x here and subtract x, and you can just here get rid of this, making it x. So you can simply divide or something. So the idea of partitioning the fraction is really, really important. So let's here do that, because as we said, we have this is common. So how can we partition the fraction? Well, of course, we need to add y square plus z square and subtract y square minus z square. If we do that, the LHS will become 1. Here, this thing will become 1 because we added like the same thing here. But because we have a sigma, it's going to get 3. And now if we move stuff to the RHS, it's going to be here y square plus z square plus x square. So basically, we can actually take sigma x square as a common factor, and it's going to be like this. All right. So it's going to be like this. Okay, is this better or this is worse? Let's put it here. Well, now, can we homogenize this? This is degree 2. Nice. Of course, this is like here degree 0. This is degree 2, degree 2. This is degree 5. Now we have only one thing that's causing trouble. If we can get rid of this x to the 5, then that's like amazing. So let's see. Can we do the same trick? X is greater than y over z. So here, we need to maximize this. To maximize it. So we need to maximize this. So the denominator, we need to minimize it. So yes, you can now do this trick. X to the 4 over yz. And now it's degree 2. So now everything is perfect. And now we're done with the condition. Okay, perfect. So let's do that immediately. So I'm going to replace this x to the 5 with like x to the 4 over yz. Or you can simply just do the following. Like say RHS is less than or equal to sigma x square. Of course, formally you should do that. RHS is less than sigma x square times sigma 1 over x to the 4 over yz plus y square plus z square. And now, of course, we need to fix that. This is equal to sigma x square times the yz here. We're going to fix this thing here. So this is actually the yz will be above in the numerator, and the x to the 4 is still there. Now we have y cubed z plus yz cubed. Okay, that looks perfect. This has degree 1, and now our goal is to show that this thing is less than 3. So now our goal is to show this inequality. I'll copy that. And now all what we're going to do is simply to show that this thing here is less than or equal to 3. Okay, now of course we don't have any condition, and we can think here about whatever we want. Of course, now how can we do this question? The plan actually here is to expand everything. How can we expand? We're just going to multiply by pi these guys, and I know what you're thinking of. This is going to be a nightmare because we have like a pi of 3 stuff. So 3 times 3 times 3, this is going to be 27 term on the RHS, and on the LHS also something similar that we have also this thing here. So it's going to be a nightmare for sure. But considering that this is an IMO problem 3, like right now, let's say you have solved problem 1 and problem 2, and you literally, if you just solve problem 3, you're going for the gold. So it is worth like that. And okay, even like if you get bored here, you should be able to solve this, because we don't have any other condition here. And of course, if we expand everything, then we should be able to apply Muirhead. This is basically the plan in our mind. Okay, so let's take the courage and go ahead and expand this. Of course, one thing that you should consider, when you expand, you shouldn't turn into a fish. Just like go and expand everything. No, your mind is still like you should use it. Don't turn it off when you expand. This is like a rule of thumb in Muirhead or in math in general. When you want to expand and do routine stuff, don't turn off your mind. You always need to like find the tricks, find some hacks. This is especially useful in like bashing problems, like bashing geometry problems with complex coordinates, barycentric coordinates, whatever. Always when you have some expansion or something like that, calculations, you should always find tricks. So let's try it now. Try to expand the usual method, and of course always if we have some nice thing, something that we can cancel, then we should always keep an eye on. Okay, so right now we're going to multiply by pi of that and the LHS and RHS, and of course see what we get. So this is equivalent to proving the following. Okay, now we're going to have x to the 4, so now y to the 4, or let's basically say of course it's a sigma, we should write the sigma, yz times y to the 4 plus z cube x plus xz cube times z to the 4 plus y cube x plus xy cube. Alright, this is the LHS. The RHS is 3, and it's of course the pi of x to the 4 plus y cube z plus y z cube. Well, you can actually say that this thing here, sigma this times x square plus y square plus z square. This is basically what we'll be doing here. Like you can take this outside or you can put it inside. It's all the same, because after all we're just going to expand this, and we want to apply Muirhead, so we want to have everything expanded. So actually even this we need to expand it. We cannot just keep it like outside. All right, so now how are we going to expand? Is the plan the following: expanding these guys 27 terms, and these guys 3 3 3 27 terms, and then we're having a sigma, so of course it's 3 times that. Well, you can do that of course and then try to cancel, but here if you think a little you can see a brighter idea, which is, notice that here we have a product of 3 things, and these things actually are the same as these guys. So for example, we have x to the 4, then y to the 4, we're going to have this, then we're going to have this. So looking at this 3 here, one idea is to try to take this guy to the RHS, and like here, this 3, we can make it a sigma, and we can take a common factor here, and maybe this times this, like we're going to subtract it from one of them. So now what's the idea? The idea is that this is going to be less in difficulty than expanding this thing. So let me show you what I mean here. I'm going to make this, okay, let's say this is 0 and this is less than, and as we said, we're going to take this as a common factor. We'll make it sigma and take y to the 4 z cube x xz cube times z to the 4 plus y cube x plus xy cube. All right, now the rest. What do we have rest? We have this one here. Here now we're going to take, okay, let's move this a little to the left. Actually I prefer to put it here. Okay, now we'll have x to the 4 plus y cube z plus y z cube. All right, this thing here. Now what do we have left here? This and this. So we need to say minus, let's expand from the beginning, yz times this. This is easy to expand. It's just x squared yz minus yz times these guys, so y cubed z minus yz cubed. And we just need to show this now. Now watch the magic. This cancels, this cancels. So at the end of the day, this is the same as showing 0 is less than. Actually, I prefer to make it like this. Let me just flip here. Here, instead of having all of that, we just have actually x to the 4 minus x squared yz. That's it all. Alright, so now we just need to show that this thing is greater than 0. Now notice that this is much easier. Look here, 3, 3, 2. So now it's actually not 27, but it's actually 18. And then we just have a sigma. So this is actually doable. We can expand this. After all, as we said, this is a problem 3. IMO problem 3. So we should, of course, not be here. Like not say that this is boring. No, we should give it our best. Okay, so let's go. So now how are we going to expand this? The idea is simple. We will take this guy here, just x to the 4, and expand these and just distribute it with them. Then we'll take this guy here and distribute it also with them. And then, of course, we'll just cancel stuff and see how can we apply Muirhead then. Alright, so let's do that. Okay, so actually, one idea is just to multiply these guys together and then just to put the x to the 4 and then put this as well. So let's try this idea actually. So first of all, let's expand these. Okay, we're going to get y to the 4 z to the 4 plus y to the 7 x. Of course, I'm just expanding the regular way like this, plus y to the 5 x cubed. Okay, we're done with that. We're going now to expand with this. Z to the 7 x plus actually now we're going to get z cubed y cubed x squared, then z cubed x to the 4 y, then x cubed z to the 5 x to the 4 y cubed z, then x to the 6 y z. Alright, that's it. Okay, this is the expansion of this here. So now, of course, we need to distribute the x to the 4, and we need to, of course, like distribute this as well. Okay, let's start by x to the 4. We're going to insert these. Let me actually copy it. And now we will just insert x to the 4. So whenever we have an x, we're just going to increase its power by 4. So here, do we have an x? No. So let's insert x to the 4. Do we have an x? Yes. So let's make it 5. Now is 3 plus 4 is 7. 1 plus 4 is 5. 2 plus 4 is 6. 4 plus 4 is 8. 3 plus 4 is 7. 4 plus 4 is 8. 6 plus 4 is 10. Of course, now everything is degree 12. Should be degree 12. Degree 12 as well. Okay. And this is basically the LHS. However, we have a sigma, so we need to do the sigma as well. So let's think about it now. This thing here is what? X to the 4, y to the 4, z to the 4. Do we have anything else? No. So it's going to be sigma of that, and the sigma of that is simply 3 3 times that. Okay, so let's, when we get rid of something, put it in red. Okay, we're done with that. Next, what do we have? We have this thing here. Use another color. Y to the 7, x to the 5. Let's look for similar stuff. This is also similar, this is also similar, and this is also similar. So as you can see here, we have x to the 7 and x to the 7, z to the 5, y to the 5. So this is going to be sigma symmetric, x to the 7, y to the 5. But also we have these guys as well. So we have actually 2 times that sigma symmetric. Okay, this is perfect. So we're going just to write 2 sigma symmetric x to the 7, y to the 5. And now we're done with that, with that, with that, and with that. Okay, perfect. What next? Let's see. Well, this thing looks interesting, as we have also 2 of these guys. So of course this is just going to give us 1 sigma symmetric. Let me grab this down a little. So plus sigma symmetric x to the 8 y cube z. And now we're done with these guys. Okay, now actually we just have the others. So it's just sigma x to the 6 y cube z cube plus sigma x to the 10 yz. Alright, my friends, this is finally the LHS. We're done expanding that. Perfect. This is our LHS. Okay, now for the RHS. So for the RHS, we're also going to multiply that by what? By x squared yz. So we need to increase each one of them by 1, 1, and the x squared by, like the x by 2. So I think we should probably copy that again. It's really important to be organized so that if you make a mistake, you can easily fix it. I hope we haven't made a mistake here. Okay, so right now we have x squared yz. So let's start here. X squared 5, 5. X squared, so cube 8 z 5 6 z 3 8 y 4 4 4 6 2 4 5 6 and a y 6 and here 4 and 2 and 8 2 2. All right, that should be it. Okay, now let's distribute the sigma, of course. The same thing. Let's look for stuff that are the same. Guess what? We still have this guy. So we actually here have 3 x y z 4 4 4. Perfect. Let's get rid of that. What do we also have? Let's look. X squared y to the 5 z to the 5. Do we have this again? No, we don't. So okay. Sigma x to the 5 y to the 5 z squared. Okay, and now we're done with that. What do we also have? Okay, let's look. This thing here, okay, it looks similar to this. Do we have it again? No. Okay, so this simply gives us a symmetric. Sigma symmetric x to the 8. Let's try to order them always. Descending order. Okay, perfect. So we're done with these guys. Okay, what next? This. Okay, y to the 6. Do we have something also to the 6 and a 5? To the 6 and a 5. Okay, here it is. Okay, alright. So this also gives us a symmetric. Okay, y to the 5, Z. Alright, perfect, we're done with these. Next, we have this 6, 4, 2, 6, 4, 2, also another symmetric. X to the 6, y to the 4, z square, and finally we just have the remaining one, which is sigma, just sigma. Let's move this to the LHS a little. Now we have sigma x to the 8 y z, okay, square square. Okay, perfect, finally this is the RHS. Okay, perfect. And now, my dear friends, we just need to show that the LHS is greater than the RHS and the cancelling should begin. So let's look here at stuff and try to cancel. What can we cancel? Well, we can cancel this with this, clearly. Do we have something else to cancel? Let's look. Here, like, comes the beauty that you basically order them. If you didn't order these, you might end up with something like this. Like x to the 5, maybe z to the 7, and you will not notice that this may be cancelled with something else. So now you should always do that strategy, x and then like x to the greatest power, y to the greatest, the second greatest, and z to the smallest. Okay, so now let's look here. Do we have something for that here? Well, for sure no. So that means this one stays. Okay, so let's say for the ones that stay, let's put them in green. Okay, next, this, do we have it? X to the 8 y cubed z. Yes, we have it. Okay, perfect, so that gets cancelled as well. Okay, next, this here, do we have it? X to the 6 cube. No, we don't. So this one stays. Finally, to the 10, well, we don't have a 10 at all there. So this one stays, and that means these guys stays as well. Okay. So now we just need to show that these guys are greater than these guys. Okay, so now how can we do that? Finally, we have like expanded, and we have just polynomials, and now it should be just a work of Muirhead, right? So now, how can we do it with Muirhead? Usually with Muirhead, right now we only dealt with 1 sigma and 1 sigma. Now we have multiple of sigmas and multiples of sigmas. So how can we deal with that? Well, for sure, we need to decide what to pick with what. Like, we need to pair them, kind of. So one strategy that's cool, because everything is symmetric here, or cyclic, of course, still, but everything is symmetric. Remember, I told you sigma symmetric is something, and if you say this thing is symmetric, it's something else. So this thing is symmetric because this here, this function is symmetric. But this is not a sigma symmetric, because if it's sigma symmetric, then it's 2 times that. Okay, anyway, right now we can actually represent everything with the sequence of powers. So for example, here, we can just write this like this. Okay, actually, let's write it the following way: 2 times 7, 5, 0 plus 6, 3, 3. But actually, it's not like that. It's half of that. And then also half, 10, 1, 1. Okay. On the RHS, what do we have? We have 5, 5, 2, and it's half. 6, 5, 1, 6, 4, 2, and half, 8, 2, 2. Alright, so this is basically our inequalities in terms of Muirhead. It's really a nice way to think about them like this. Now we will think, how can we pair like these guys together? So right now who is like great and who is small, who is large and who is small. Let's see. Okay, this one is really a monster here, and this one is also good. This one is the worst for sure. 633 is not that much. Here, who is the monster here? Clearly this guy is the monster. And we have this 651 is the second one, the third and the fourth. Okay, so let's look. Can we pair the smallest here with the smallest here? 6 plus 3 is 9. 5 plus 5 is 10. Oh, we're screwed. Why? Because this is the smallest here. So the only way like it should do is the smallest should beat here the smallest. However, no, it cannot. So unfortunately, we cannot just do Muirheads here. So what does that mean? Are we just screwed? No. This for sure should be correct, this inequality. But that means that Muirhead alone might not be enough. Okay, if Muirhead is not enough, what should we do? Well, remember, you can still apply AMGM. You can still apply AMGM, and even in this form, you can apply AMGM. How? We can, for example, mix one here with one here, and if you want to apply AMGM, what are you doing to the powers? You're just adding the powers and dividing them by 2. You're taking their average. So, for example, if you mix one of these plus one of these, you can think about it and notice that it's actually greater than. Okay, 16 over 2 is 8, and also 4 over 2 is 2, and another 4 over 2 is 2. So it's like this. So we can actually mix these together and get one of these. Notice that it's going to beat this and even get a half remaining. Okay, so this seems a nice idea. So what does that mean? That means we're going to replace this here by AMGM, replace it with this thing here. All right? Okay. Not to confuse ourselves, let's copy this. Of course, right now this writing is not formal. You should not use it in a context. In context, really, we're doing it on draft, just to know like how to think of this, how to apply the AMGM or Muirhead. So our plan is to do something like this: 2, 7, 5, 0, plus instead of these guys, we're going to write 8, 2, 2. Now, our goal is to make this beat this. How exactly can we do that? Well, as we said, this will cancel with one of these. So now actually we just need to show these guys with only half of this. So we want these guys to beat each other. Okay, how can we do that? Well, this is everything now here is good. Let's see. So this thing here actually, who is the greatest here? This 6, 5. This is 11. Let's see. Here, this is 11. Oh, so actually, we can now do this pairing. This with this, half with a half here. Okay, these eat each other. And now we can take this as 2 copies, 1 copy here and the other copy here. And make sure that we have the majorization. For sure, 822 majorizes 552, for sure. And 750 for sure majorizes 651. You can check. 7 is greater than 6. 7 plus 5 has everything, so that's enough. And also it majorizes this. So actually, that's it. We're done. We have solved the IMO 2005 problem 3 using Muirhead and just the simple AMGM here in order to take care of this one, because it's too small. We need to let it borrow some power from here, and now everything comes smoothly. Alright, so as a summary, today we solved 2 problems with Muirhead. First of all, we solved the first inequality. We proved Nesbitt's inequality, the very classical standard inequality. The plan was really simple. This was some fractions. So we need to expand this. How can we expand it? We just need to get rid of the fractions, multiply by pi b plus c both sides, and expand. This is easy to expand. Just like do the regular expanding, and always do these tricks, like this is symmetric, so if you just get a square b, you should get the other sigma symmetric, and always double check for the counts. Like how many do we have? So for example, here we have, if we expand this, we're going to get 4 numbers, because 2 times 2 times 1 is 4. So 4 times 3, because we have sigma, it's basically 12. And let's check here, 3 plus 6, it's indeed 12. The same thing here, by a plus b, it's just like 8 here, and here we have 6 plus 2, so it's indeed correct. Okay, after that we simply just expanded, and we ended up with this 300 majorizes to 10. This is correct, of course, by Muirhead. Right now we're done. Next we solved the IMO, problem 3, 2005. We have 3 numbers, x, y, z, positive, and their product is greater than or equal to 1, and we need to prove this inequality. So our goal was really clear. We need to homogenize the inequality by getting rid of the condition. Well, we faced one problem, that we have x to the 5 here and here. We can get rid of this, but we cannot handle this. So we thought of one very, very important idea that should always come to your mind, which is partitioning the fraction. We partitioned the fraction indeed, and we got this. Now we have just a single x to the 5, and now our trick works for homogenization. So we homogenized it, and we forgot totally about the condition. Now we simply need to show this inequality, and now we simply move to the nightmare of expanding. We expanded nearly everything here, but then we noticed a very, very useful trick here, which is that instead of simply expanding everything immediately, we use the idea, or actually here it's 3. We use that idea that we have here 3 of this. So we made it a sigma, and we took 2 of these guys, like these basically, and we moved it to the RHS, and luckily we canceled lots of stuff, and we got this. So now it's really easy to expand. Now it's just 3 times 3 times 2. Okay, and then we just moved to expanding. Of course, we did this nice trick. We just expanded these guys here. This was just their expansion. And then we just multiply this and then multiply this to get the LHS and RHS. So to get the LHS, okay, we did that easily by just expanding the x to the 4. We got that, and then the RHS the same. And then we simply look at them and cancel stuff. And then we, instead of thinking about them in this way, we just thought about them in terms of powers. We just care about powers after all, since everything is symmetric. So we thought about them in this style, and the Muirhead alone was not enough because this guy is too small, cannot beat the smallest thing here. So we mixed it with that guy using AMGM. This is really not that crazy move here. Like basically it's the only way to handle this, since Muirhead will fail here. So after we did that, luckily we got 2 actually of this, or simply just 1. But then when we paired it with this one here, we got just half, and then we just paired stuff with Muirhead, and we are done. So I hope you guys enjoyed this, and you can see now the power of Muirhead. Muirhead is really like useful. In a sense, it's a special case of AMGM, but in another sense, it's really sometimes it's even more powerful than thinking in the regular AMGM. Although they are also like they always come together. As you saw here, we applied AMGM and then applied Muirhead. So I hope you guys enjoyed this video. Please like, share, and subscribe to my channel, and see you guys in the next video.